Hello, everyone, and Happy New Year. Unfortunately, I tested positive for COVID, so I'll be out probably until Wednesday of next week. Until then, I'm going to be recording some videos, and I'll put the set of notes online for you to go through, and I'll put a problem set up once we're at that point. Today, I didn't realize that we were starting with fourth period, so I'm starting this video a little late. It's like a half an hour before period 5. So I'm going to get through probably like 10 or 15 minutes of this, and then I'll tell you which example problems I want you to do from the notes, and that'll be your work for today. I'll put up a new video tomorrow with more instructions. Okay, so this is our next unit is going to be on momentum. This is going to be a fairly short unit. It's probably going to take us about 2 weeks, and then we're going to move on with stuff. When I get back, I'll talk about a project that you're going to be working on in groups. It's going to be to either build something that'll protect an egg, sort of like an egg drop experiment, but I'll give you more details on that. Okay, anyway, this is what we're going to start off with today. So our unit is on momentum, which you've got sort of a general idea of from the outside world, because we use that term a lot. You can think of like something with momentum is difficult to stop. So momentum is it's like how difficult something is to like bring to a stop. Our physics definition of it is given by, we call momentum P, and then we say it's the mass times the velocity. So if something's heavier, it's going to be harder to stop, or if it has more velocity, it's harder to stop. Okay, so momentum is the difficulty of stopping an object. Okay. Its more precise definition is this. So if you look up like the physics definition of momentum, they're just going to give you this. They won't actually give you a description in words. But we'll go through a couple examples, and hopefully that'll make it a little more clear. In this expression, P is the momentum, V is the velocity, and M is the mass of the object. These examples will kind of give us a clearer picture of what has more momentum, what has less. A bowling ball moving at the same speed as a basketball has more momentum because it has more mass. Okay, so we can imagine using this equation, trying to find P. If we say that V is the same for each of them, say V is like 5 meters per second, the M for the bowling ball will be a bigger number, so P will end up bigger for the bowling ball than the M for the basketball, because that'll be a smaller number, so P will be smaller. That means that the bowling ball is going to have more momentum because it has more mass. Okay, and then for this one, a bowling ball moving at 15 meters per second has 3 times the amount of momentum as a bowling ball moving at 5 meters per second, assuming they have the same mass. Okay. Again, that's because our definition of momentum comes from the mass times the velocity. So the more velocity something has, the more momentum it has. If it has 3 times the velocity of another thing, then it's going to have 3 times the momentum. For objects, you can think of momentum as how hard it would be to stop a moving object. If an object has lots of momentum, it is hard to stop. Hard to stop. Okay. For the units of momentum, I want you to go through and try to do that by yourself. So look at our dimensional analysis portions of our other notes and figure out what set of units would work for this. Okay. It's going to be one of these 4, and you can kind of look at it like, what are the units of mass? What are the units of velocity? And then just multiply those together. Momentum is a vector. And it has the same direction as the velocity of an object. So we treat like a momentum going this way different from a momentum going that way. So unlike energy, we actually have to keep in mind the direction of the momentum. There's going to be a lot of like parallels to energy in this. The biggest difference is that it's a vector instead of a scalar. Other than that, it also has to do with time instead of with distance. So we learned about with energy, to change the energy of an object, we have to do work. And work is given by force times distance. Okay, so force times distance, or F times delta X. Okay. The way we change momentum of an object is by giving it an impulse. So that's our equivalent. So instead of doing work, we do impulse, which is given by force times time. Okay, so we had force times distance. Now we've got force times time. All right. Impulse equals the change in momentum. Sometimes they'll give this a variable of j. We're not going to do that too often. I'll just call it an impulse. But if you take engineering classes down the road, they'll say that j means impulse. That can get confusing with joules because the units for impulse are not joules. They're the same units as momentum. All right, just how energy and work were both given in joules. Momentum and impulse are both measured in, and here I'm going to give you the answer for up there. Hopefully you were able to get that. Kilogram times meters per second. Okay, kilograms are mass, meters per second is velocity. So the unit is kilogram meters per second there. Both impulse and work can be used to understand the physics of slowing something down. So you can either think of it as something that has energy that you're trying to get rid of to bring it to a stop, or something that has momentum that you're trying to get rid of to bring it to a stop. If you know the distance over which it has to stop, then you can use work. If you know the time it has to stop, then you can use impulse. But again, work and impulse are similar. One has to do with distance, one has to do with time. Okay. We're going to do, I'm going to do probably the odds, then your assignment for today will be to do the evens in this note sheet. I'll upload it online. Okay. Baseball with mass of 0.145 kilograms travels at the speed of 35 meters per second. What is its momentum? So we'll just use our formula for momentum, which is P is equal to mv. Okay, so P would equal 0.145 times 35, which is equal to 0.145 times 35. 5.08 kilogram meters per second. Okay, that's our unit. There's no one letter unit for it. Okay, car has a momentum of this and a mass of 1,100 kilograms. How fast is it moving? Use the same equation, P equals mv. So I'd get 4,500 is equal to mass is 1,100 times v. Looking for v, so I'll divide by 1,100. I get v is equal to 45,100 divided by 1,100. Okay, 4.09 meters per second is our unit for v. Okay, bicyclist, so how much force would it take to stop a car from problem 3 in 1 second? Okay, so this is our momentum. We're trying to get it to stop in 1 second. So we're going to say that impulse, we're going to say that our change in momentum is equal to force times time. So again, force times time, that gives us our impulse. Our impulse tells us our change in momentum. Okay, so our momentum, we're going to start off with, that's going to be P final minus P initial. So again, every time you see delta, that's final minus initial. That's going to equal force times time. So we'll go up here. Now our final is going to be 0 minus 4,500. That was our initial. That'll equal force. And then times 1 second is our time. So force times 1. Okay. So then we just get negative 4,500 is equal to F times 1. Just divide both sides by 1, which doesn't change anything. So we get 4,500 newtons is our force. Okay. That negative sign means that our force is in the opposite direction of our momentum. So if we called our momentum positive, like this had positive momentum, then our force is going on in that direction. Okay. Then I'll do number 7. Again, what I want you to do for today's class is 2, 4, 6, and 8. A force of 200 newtons is applied to a 5 kilogram object for 1.2 seconds. It started at rest. How fast is it moving after the 1.2 seconds? Use the same thing. Delta P, change in momentum, is equal to force times time. Okay, so that means P final minus P initial is equal to force times time. P initial, it says it started at rest. What that means is our velocity is 0. If our velocity is 0, then our momentum will be 0. Because if we do 0 times the mass, we get 0. So what we end up doing is PF minus 0 is equal to F times T. So we get PF equals F times T. Now I'll plug in my numbers. So for PF, that'll be the mass times the velocity at the end. So I'll say is equal to force times time. And I know my mass, I know the force, and I know how long I'm giving that force over. So I'd say 5 times VF is equal to 200 times T is 1.2 seconds. 1.2. Okay, so 5 VF is equal to, that'd be 240, and divide by 5. We get VF is equal to 240 divided by 5 is equal to 48 meters per second. Okay. And that's it. Yep. So that's what I want you to take a look at today. We'll probably have a little bit more involved of a lesson tomorrow, and I'll probably send out the problem set for it. Good luck, and I'll see you again next week.